So here at Red Wave Labs, we developed quantum technologies, and a lot of quantum technologies are based around lasers, which control atoms, and we need very precise lasers. So in here we have what's actually just a standard diode laser, similar to laser pointers, but a very precise wavelength. And then we would feed it through this optical system here, which would have a reference cell, which has some atoms in there, and then a photodetector here, and some electronics which would make sure that our laser is locked to these atoms. And then some of that light would be sent off into a quantum computing experiment or into a quantum sensor. This one is particularly designed for a quantum inertial sensor, which is used as a replacement for gyroscopes in navigation. Another thing we develop here, and this has been in collaboration with CERN, so they developed the chip here. This device can sense events with a picosecond accuracy, so that's thousandth, billionth of a second, and very precisely tell you when your photons arrive. And this is very important in quantum cryptography, where you need to know that the photon you arrived is the one that was sent from the person trying to send you a secret message. We said it's possible that the cosmic microwave background, this radio signal from the very early universe, is still out there traveling through space. And it's actually possible to receive it with very simple equipment. So in the old days of analog television, your analog television actually picks up this signal. And although it's been shifted in frequency into the gigahertz, so a little bit higher than maybe what your mobile phone would use, there is still a very weak signal there. And so with the right antenna and what we call a software-defined radio, which is a computer-based radio receiver, we can actually pick up that signal. And some people would say, well, it's very hard to see because you've got noise from other electronics, so your receiver will pick up similar signals. However, you can plug in an antenna, a very high gain antenna, and by pointing that into the space, into the sky, you can actually show that the signal's coming from there and not from other sources. So although it's very weak and it's a very small signal, it is possible to pick it up with.
And what is it that we're hearing through that machine?
So that signal started life the very early stages of the universe. So just after the Big Bang, a few thousand years, when the universe was cool enough for light to actually escape, the light was very shifted into the infrared, so it was heat, infrared light. But as the universe has expanded and cooled, that light becomes a radio wave until eventually now it's peaked around sort of 20, 30 gigahertz, and we're detecting it at about 3 gigahertz.
Is time real, and what are we measuring?
So time has quite a complex understanding. So we think of it in modern physics as a dimension along with the 3 dimensions. General relativity, as discovered by Einstein, shows that time is actually a dimension that can have a curvature to it in the same way that spatial dimensions do. However, people have questioned other forms of time. So some researchers have asked, is it possible to have 2-dimensional time? Why only 1 time dimension when we have 3 space dimensions? Could there be more time dimensions? And what would that even mean? How would we experience a second dimension of time? Other people question why time always seems to only go forwards, and that's related to thermodynamics, but why should we not be able to go backwards in time? And it has been proposed by many researchers that maybe this is just a problem with us as humans or the current place and time in the universe, and that maybe it's possible to go backwards in time in other situations. So time remains a very mysterious thing. And I think general relativity gives us this idea of how to look at the universe in a 4-dimensional space-time way, but it doesn't answer why time is special, why it's different from the other dimensions. So there's a lot to understand. And when we think about our own experience of time, it's very subjective. We often experience time going fast or going slow, which is already an oxymoron, because when you say something's going fast or slow, you're saying how it relates to time. So how does time relate to time? What is a second per second? It doesn't really make sense. But we obviously perceive time in a very personal way, and it could be possible that the universe is actually everything's happening all at once, and it's only our perception of time that gives us this idea of flow from one moment to the next.
Do you tell us a bit about the timelessness of information?
So the current quantum theories don't have time, so they are time reversible. So in quantum computing, we make use of this idea that all the gates are reversible, and therefore they're not expending energy. So I said before, time is related to thermodynamics, which relates it to using up energy. So in a normal computer, you can feel in this room we're surrounded by electronic equipment, it's generating heat. Every time information is erased, you actually generate a small amount of heat. And our computers are incredibly wasteful. In fact, 1/5 of the US energy budget is just servers like Google and Microsoft wasting heat out into the outside universe. So it's actually a big problem for humanity that we're burning a lot of energy destroying information. And in a quantum computer, the idea is you don't burn any energy. Because it's time reversible, this also leads to the idea that a quantum computer shouldn't use any energy in its computation. Of course, you get nothing for free, so there is a little bit of energy when you read back and you want to get the result out of your quantum computer. But the hope is that eventually quantum computers will be much more efficient than classic computers. However, currently, the irony is to even do a simple quantum computation requires vast amounts of equipment, lasers, electronics, and a whole room full of vacuum containers, vacuum pumps, cooling systems, and this is all to protect the quantum information from the outside world. But in theory, the quantum system is time reversible and energy, not using energy at all.
What are you most excited about?
So I think a very interesting bit of research when I was researching in Zurich came up, which is what do we really mean by temperature? So it's a very interesting question philosophically. We talk about thermodynamics and we talk about this second law where entropy generally increases in universally across the whole system. However, we have a very ill-defined idea of temperature, and I think this has really interesting ramifications for our understanding of both time, because that's related to this energy, and quantum mechanics. And people who are now working on quantum computers are very interested in keeping their quantum computer cold. It's very important that your atoms or your system inside doing the quantum things are cold. We're learning a lot now about temperature and what it really means and how that interacts with information. And there's even a relationship with black holes and what happens with information on the edge of a black hole. So Hawking famously debated with Penrose and others whether the information at the edge of a black hole is erased or not. And the term came, do black holes have hair? By which he meant, like human beings can be identified by their hairstyle, you'd be able to identify each black hole by the information it was emitting as it collapsed. And this is still an unsettled debate. There's been a lot of research done on it, but it could be possible that the black hole is one place where information really is destroyed. Current theory suggests that the information gets stuck on the edge in a holographic way. So the edge of a black hole is actually a hologram containing all the information about everything that's fallen into that black hole. So like I said earlier, if you throw books into a bonfire, you haven't got rid of the information, you've just put it up into the ash and the smoke. Same way, when a black hole sucks in things and destroys them, it doesn't get rid of the information, it just puts it out on this edge in this complex holographic information storage. So these things are very interesting, and I'm very excited to see what comes out of them.
Yeah. Thank you.